So before we break, we cover the conversion of these three equations. We show you the derivation of T star divided by T0 equal to this form. And by using isentropic or ideal gas equation, you can rewrite them in the same form. You will get pressure ratio and density ratio. Next, we're going to look at what happens if you change the area, the cross-section of the flow. Before we move into more detail, recall the definition of continuity or conservation of mass. Conservation of mass, talking about m dot. All right, mass flow rate equal to rho AV. This is a very, very important equation for this module. M dot equal to rho AV. How to get your Q, volume flow rate? You take the area times velocity. So this is how you get your Q, how you get your M dot, and so forth. So I give you some comparison side by side, as you can read from the slides itself. So on the left-hand side for compressibility flow, density will be constant because you cannot compress it. So density will be the same. Velocity from one section to another one will inversely changes with cross-section area. Okay. What does it mean? Okay, let me go back to this one. So if you have a compressibility effect, compressibility scenario, usually happen Mach number less than 0.3. Okay, so since we are using conservation of mass, m dot equal to rho AV. If you cannot compress density constant, right? So if you want to find the velocity and the area relationship, how you write the equation? You rewrite the equation. Velocity equal m dot divided by rho A. So basically, when you read the equation, you will see that the velocity will be inversely with your area. Okay, will be inversely with the area. This is what this sentence means. Okay, so when you rewrite the equation, you get this equation. On the right hand side, if you're having a compressible flow, meaning your Mach number more than 0.3, when you're able to compress, density change, cross-section change, flow velocity change. So this one change, area change, velocity change. Okay. Recall second Newton law. Second Newton law apply when you have a non-friction steady flow. Okay, non-friction steady flow. And you're having this Bernoulli equation again. You can see the Bernoulli form, pressure, kinetic component, potential energy component, half rho v square plus specific weight and the height elevation equals 0. Okay. So this one, you see this one in the first session. So for ideal gas, the potential difference you can ignore, because for ideal gas, the elevation is very, very small. Okay. So from here, you rewrite the remaining equation. We call it approximate equation of motion. You can write in this form. In the pressure over density velocity square equal to minus the changes of volume, not volume, velocity divided by velocity. Okay, you rewrite this Bernoulli equation. put them in the ratio form of the velocity ratio form, then you get this form. Okay. So now the objective of the following slides is to derive the d over v velocity, the differential equation for velocity in terms of area and Mach number. So how do we do that? We start with conservation of mass equation, m dot equal to rho av. So because we see the final term is in terms of something divided by something, with this one will give you the logarithm ln equation if you want to get this form. So we rewrite the conservation of mass in terms of ln equation. So ln rho plus ln a plus ln v, basically what you get, you still get back rho av. Okay. Again, if you forget what is ln operation, please flip back your advanced mathematics log chapter. Okay. Next, you do differentiation. You differentiate them. You can write in terms of d rho density. The first one is density. The second one is area. The third one is volume. Okay. So this one is in long term. When you write in differentiation format, they will become this way. Okay. And then you rewrite them in velocity terms. You put the dv to your objective. You pull to the right and you rearrange the equation. So positive become negative. So negative dv over v equal to density plus area. Differentiation of density plus differentiation of area. So I pull the equation up. You get this one from m dot equation. This one we derived earlier by ignoring the gamma dz from the Bernoulli equation. This one from Bernoulli equation. The top one is from continuity equation. You combine these two, you combine side by side, you actually get the relationship between pressure, density, area. That's why you can see the one that I highlight with the yellow color rectangular here. So you can write dp over rho v square equal to density and area differentiation. And you move around the equation. This one, you move to the left, you get negative. This one. Okay. So just a side note. We want to keep the equation in terms of pressure. So how do we rewrite the equation if you want to keep in terms of pressure? We rewrite the dp equal to d rho. This is rho density. We write equal to dp over d rho. So actually it's the same thing, only mathematics, you just add in the similar term inside there so that you can substitute inside the equation. You get this form. Okay, you substitute this mathematics term here, this one, substitute inside, rearrange, you get the third equation. Recall definition of Mach number, and there's one more a definition for speed of sound where you can take as a partial differential of pressure divided by density. Okay, these are two you need to recall. So you substitute the equation, and this alone, this equation, earlier we can write as dp over the v square 1 minus Mach number square equal to dA over A. Okay. So this one, actually defined by this equation. So C square root of rho P divided by density equal to C. So C square equal to differential of pressure divided by partial of density. You pull this definition over here, you get V square over C square. Again, V divided by C, you get Mach number with a square. So Mach number square, this whole thing, rewrite at this one. Okay. So next one, you replace this one over here. And then you move the Mach number to the right hand side. You rearrange with this one, substitute here. This one, you rearrange, it becomes a V form. dV over V, this is velocity, equal to negative dA over A, 1 over 1 minus Mach number square. Okay, so we are having equation, this equation here. Okay, we just derive this one. And this one is the earlier we derive from continuity equation. Remember just now, Mach number changed to log. Then you differentiate it, you get this form. Now you combine these two equations. You take the first one minus, take the first one plus the second equation, means you cancel out the equation. And I pull out some of the equation that you learned previously. So if you first equation plus the second equation, you cancel, you get 0. On the right hand side, you get 0. That's why you get 0 here. Then this one plus this one, you'll get this form. Okay. You get the remaining form, this one. Then you focus on the right hand side. We rewrite the equation in terms of density. You move this one to the left hand side, and you will see your density differentiation equal to this form, equal to this equation. You pull the A together, we rewrite again the equation. Okay, it's the same equation, but we rewrite again. We recreate a new terms in the equation, which is this one equal to 1. You can see, right? 1 minus m squared divided by 1 over m squared, you get 1. So basically, you're creating something, you're manipulating the equation. So 1, you rewrite because we want to do something about the term in front. So 1 over ma squared, we want to make something that's similar to the second term. So we recreate or we manipulate the equation with 1 over Mach number square divided by 1 over 1 minus Mach number 2 power 2. So at the end, you can rewrite the equation in this form. Okay, so you can rewrite, you simplify this equation, you'll get d over dA, then Mach number square divided by 1 Mach number square. Okay. So what happens if you have a subsonic flow over here? what happened to this equation? You see that when you have a very small Mach number and very small number, so if the Mach number is very small or less than 1, or in the subsonic, that you can see from the equation above, the density and area will happen in the same direction. What does it mean? It means if you change A, something will change to density here. Okay, if you change A, something will change to this one, and so forth. However, if you have a Mach number, if your Mach number more than 1, what happens? If you have more than 1, then you get a negative value for this term. If your Mach number more than 1, now it's just mathematics. If you look at Mach number value more than 1, 1 minus more than 1, you get a negative value of this one. So the total component here, you get a negative. So negative on the right hand side, it means the density, the parameter that you see inside here, they actually opposite of each other. If you change area, if you increase area, density will drop, and so on. However, Mach number equal to less than 1, if you increase density, area will increase, and so on. So this is basically playing around with this mathematics model here. Okay. So giving you this diagram by explaining what happened to the Mach number. Mach number less than 1, more than 1, what happened to these two? I put in a diagram, and maybe you need to start to learn what is diverging. This is called diverging. Diverging means small area into bigger area. Okay, small area into big area. What I mean by area? This one, this area to this area. Is called diverging duct. So if you are giving the opposite one, from a big area into small area, we call it converging duct. Diverging, converging. Diverging, converging. Converging, diverging. Okay, converging, diverging. It depends how you memorize lah. I memorize by this shape lah, this face shape. Okay, I draw the face, I put a C, I put a D, I draw a circle, I get a face to memorize what is divergent and convergent. Okay, so you have your own way of memorizing the English word. This is how I memorize. Okay. And all these you can see from this diagram. What happened if your Mach number less than 1, basically is still explaining the equation just now. Mach number less than 1, area will increase, velocity will drop. Okay, and what happened to the Mach number more than 1? Your area will increase, velocity will increase. However, what happened to converging case? Converging case, if your Mach number less than 1, area, in this case, because it's converging is big to small, so area will be smaller, and the velocity will increase. Okay, velocity will increase. And what happens if you have a supersonic flow in the converging duct? Area still the same, area still, because it's converging means big to small, the changes of area will be smaller, will be negative, less than 0, because it's smaller. You take something small minus big area, you get a negative value, right, for area. So area less than 0. Velocity will be decreasing also. Now, how do you memorize the area and velocity? First, I memorize by diagram. This is converging, this is diverging, right? And I draw a face, right? So it's an angry face. So you have a converging. Converging means you have a big area to small area. In this one, this is converging. So imagine you are the flow. You actually squeezing. You're actually squeezing yourself throughout this one. So velocity increase. When you're having a Mach number, a subsonic flow. And then supersonic is the opposite. Velocity will be the opposite one. Same with this one. Same with this one. So if you're escaping from small area, from a diverging scenario, diverging means small area to big area. You imagine you suddenly exposed to a bigger space here. Your velocity will drop. Velocity will drop. If you running from small area to a big area, your velocity will drop at the Mach number less than 1 or subsonic scenario. Then the supersonic will be the opposite one. So this is how you memorize the effect of cross area to the flow. Okay. All right. So this is called, again, this is converging, diverging duct. This is a converging, this is a definition of small to big, it become diverging. Big to small become converging. So this diagram A on the left is converging, diverging duct. On the B diagram here is diverging, converging duct. It's important, you as an engineer, later on, don't mix between the converging, diverging, and diverging, converging duct. You are going to hurt someone if you describe wrongly or you design wrongly in your design. You're going to hurt someone. Okay, someone going to die if you're not careful in this shape. Okay, so be careful. You are an engineer later on when you work. Okay. Still call back to this general equation and the diagram that we just covered just now. So yeah, this is just an elaboration. I'll go very fast. You can read from my slides. So this is a table for you to check whether you get the correct answer or not. If you're having a converging passage, means big to small passage, the changes of area will become smaller, right? So, or less than 0 because you are taking the area 2 is small, right? Area 2 minus area 1, you get a negative area. So that's why the changes of area is negative for the first one. So this is how you check when you have a Mach number less than 1, velocity increase. So imagine you have a big area into a small area, you need to travel fast. So V increase and so on. So this is a table to help you to check your answer whether correct or not. Okay. So just a quick answer, quick question. Is it possible to reach Mach number 1 at the center of the duct? Here, at this location. It is possible to reach Mach number 1. Is it possible to reach Mach number 1 at this section? Is it possible? If the upstream velocity is subsonic, if the area of the Mach number at the entrance here is less than 1, means subsonic flow over here. Have a thought. Think about this one. The answer is that this one is possible. This one is not possible. Okay, look at the equation and the table that I just showed you just now. It's going to explain this question. Okay, you're going to come across this question when you go to work, especially you have a converging, diverging scenario. Okay, you cannot run away as a mechanical engineer that you build something that having a flow around it. Okay, so have a thought into that. Okay, so these are the explanation on whether it is possible to reach Mach number 1 at the center, while it's not possible for the second scenario. Okay. So these are the equations that we use to prove the question. The rest you can read. The next one is on the calculation for the converging diverging duct. We will use stagnation states and also we use stagnation states to calculate. So let's look at one example. So these are the calculation that we're going to use. Okay, so this one we already explained why in ideal gas equation we take out the potential energy equation from the Bernoulli equation. Okay, so these are the equations we're going to use later. So these are derivation. Sometimes you use this equation, sometimes this one, sometimes this one. This one is when Cp value is given, you use the third one. If you do not have Cp value, you have the K value, R value you can find. And actually it's a conversion from pressure density to temperature equation. So it depends on the scenario that you have. Sometimes you have pressure, you have the pressure and also density parameter, but you don't have temperature, so you use the first one. If you have a temperature, then you use the second one. If you have the Cp value, then you use the third one. Okay. So all these are derivation of equation. This one is enthalpy equation. We apply the same concept from the Cp times the T0 minus T equal to V squared divided by 2 equals 0. So derivation you can read from the slides. Okay, what important is the application of equation? So here we have the enthalpy at stagnation pressure, stagnation scenario, H0 minus H plus V squared divided by 2 equal 0. So the rest is you can find the screen, and you have the more complex T ratio equation. T divided by T0 equal to 1 over 1 minus K minus 1 divided by 2, Mach number 2. And then you use the T ratio, you can find the pressure and density ratio using the conversion. Okay. This is the equation that I refer to. So you are using this conversion. Use back the T equation just now, this one, to form the P ratio and density ratio. Okay, so these are the derivation step is on the right hand side of my slides. So these are the temperature and entropy diagram that covered in the thermodynamics chapter or module. So you should know how to plot the T and P diagram from here. Okay, so this is just a recall from what you learned in your thermodynamics. This straight line is isentropic lah, okay, because the S value is same. These are just to repeat what we covered by the previous slides. Basically is the temperature ratio, pressure ratio, and what is the differences is the exponential over here by doing the conversion. When you study about conversion divergent, there's one scenario called choke flow or critical states. Okay, critical state, just now we mentioned your Mach number equal to 1. Or sonic flow happen inside the duct. So if you have a shock, sonic shock, then you have a shock flow inside the throat. This one happen in converging, diverging duct. So I'll go very fast. This one repeated already. Still, you're still seeing the same equation. And the rest is just conversion. So let's look at this tutorial and then we sum up this chapter. Okay, so if you look at your diagram on your screen, you're having a converging duct and a receiver pipe here. The flow is flowing from the left to the right. Okay, so if you read the statement above, the throat minimum flow cross-section area is given here. The area is given. Area is 1 10 power negative 4 meter. Area is given. Receiver pressure A and B is different. So you have two scenarios. First scenario, your pressure inside here, first scenario is 80. Then after you solve for 80, you go solve for second scenario. What happens if you have a 40 kilopascal scenario? Okay, then you need to know how to plot T versus entropy chart from this question. Okay, so you need to plot what happened to the A scenario when the internal pressure is 80 kilopascal. You need to plot on this chart and then repeat the same, plot 40 on this chart. Okay, so what are the strategy we use to solve this kind of question? First, you need to calculate the mass flow rate given by rho AV. I think this one you expert already, m dot equal to rho AV. So since we are given the parameter at the throat here, so we just modify a little bit our equation to calculate the mass flow rate at the throat here, this area. So we just sub m dot sub th mean at the throat there, and all the parameter is at the throat. So density throat, area throat, velocity at the throat. So recall, since we are need to find the velocity at the throat, we can use the Mach number definition. Okay, so I keep repeating asking Ku just now, and I asked Dinesh just now about definition, and Shirley helped to answer also on the Mach number definition. So again, is important. Then you rewrite in the equation to find the velocity for the throat. You take these two equations, put inside there, you get one new equation. Okay, so you have a new equation for V throat. After that, recall that you have three equations, the T ratio, P ratio, and density ratio equation with the Mach number term. Okay, so you can see actually the middle one is the same. The middle one actually the same. What is different is the exponential component. It's different if you convert temperature, pressure, and density. So we modified according to our question. We modified the left-hand side equation to the throat condition. So the throat condition, the temperature here actually defining the Mach number. So if you're changing the throat here, the Mach number here also following the throat condition. So as you can see, there's a modification of equation. T become T throat, Mach number become Mach at throat. You do the same for other two equations. Pressure at throat, Mach number at throat. Density at throat, Mach number at throat. So we just modified from the left-hand side to right-hand side. So we focus on these three modified equation. So you can see that for a throat at the K equal to 1.4, P star divided by P naught at K 1.4, okay, equal to 0.58. Okay, how do we get this number? There's a derivation steps for this number. You go back to my slides and read through. This one slides explain about this one. This one, okay. So go and read the slides. So for air, K1.4, the P over P naught equal to 0.58. Okay, P star. Or you can go to the appendix D. You go to either use this chart. You go to Mach number 1. You project up. If you want to find the pressure, you project up. The first line is area. The second line is pressure. So you project up. You move to the left. Right? You move to the left. It's about 5 point something. Okay? You can see, right? Mach number 1. Project up. Again, the number of Mach number 1 is the sonic scenario. So you move up, touch this point, move to the left, you get pressure ratio, which is 5 point something. Okay, you get 5.28 lah. Okay, or if you go to this chart, table DI, Mach number 1, you move to Mach number 1 here. You can see the number of the P over P0. The value is 0.5283. So straight away you can use the value from this table when you have a Mach number 1. So it already highlight in the appendix here already. Okay, 0.5283. So straight away in the question of this one, you can straight away use 0.5823. Okay, you can use the value of 0.58528. You rearrange, meaning you pull this one P0 as a atmospheric pressure. So you have P star, value of P star will equal to 0.5, P atmospheric will equal to 0.5 stagnation pressure. Okay. You substitute the atmospheric pressure. Atmospheric pressure on this earth is 101 kilopascal. So the pressure star means Mach number or critical pressure, Mach number equal to 1, will equal to 53.3 kilopascal. Okay, once you get your P star, you can find the remaining one. Okay, so the scenario, if the receiver pressure here, this is your receiver pressure, RE. You know that your stagnation pressure, P star, you see the marking of P star means the Mach number equal 1, or we call it critical condition. If the value of pressure is more than this number, the throat will equal to pressure at here will equal to receiver internal pressure here. This happens when the PR receiver value is more than P star. Okay. What happens if you have another scenario when your pre-receiver pressure inside receiver is more than your critical pressure? Then your pressure at throat here will equal to your critical pressure. Okay, so there are two scenarios. One is internal pressure more than the critical pressure. Internal pressure of inside this receiver less than the critical pressure. Then you can estimate the pressure at the throat here. You can estimate pressure at this area. Okay. So if you have a P star, if your P throat equal to P star, meaning this one, you have a Mach number equal to 1 here, you having a shock wave over here. This phenomena you have a choke flow. You will choke your flow here. Okay. Another one is just recall from the thermodynamics. Stagnation temperature at the standard atmosphere equal to 15 degrees C, standard temperature, 15 degrees C. However, in this case, we are using Kelvin because when we use the isentropic equation or ideal gas equation, or we deal with Mach number equation, C equal to square root of RTK. The R value here is in Kelvin, so your temperature must put in Kelvin. Huh? Just take note on that. Okay, so I already explained. And also you are looking at isentropic, so isentropic entropy also in the Kelvin unit. Okay, it's just a highlight for you. So what happened to the first case? If your receiver pressure 80 kilopascal, your P star is 53.3. What is the scenario at the P throat here? All the information is on this slide. So I'm going to ask question. Shirley, what do you think? What do you think if your internal pressure is 80 kilopascal, it fall under which scenario? Scenario 1 or scenario 2? Shirley, are you there?
Yes, sir, I'm thinking.
So, okay.
It will fall under the first one.
The first one. So, first one. So, what happened to your P throat? P throat equal to what? Based on the slides. What happened? If you scenario 1, what happened to your P throat?
To the is equals to P star.
Oh, you are having this first scenario, right? So this first scenario give you this one, right? So this one equal to what? P throat equal to P receiver, not P throat. P star is the next one. P star is the scenario 2.
Yes, yes.
Okay, good. Raj and Dinesh and Ku standby. I'm going to ask you the second scenario later. What happens if you have a B scenario? Okay. Or maybe I ask you now lah. Cool. Second scenario is 40 kilopascal. It's fall under which category? Under which scenario? Scenario 1 or scenario 2? Who?
Scenario 1.
scenario 1. Do you understand these two statements or not? Do you understand what I mean by 1 and 2?
The first one is higher and then the second one is lower.
Okay. So now your case, you are answering B now. B. I give you B. Now your B case is P receiver now is 40 kilopascal. And your P star, what is the P star value?
Oh, 53.3.
53 kilopascal. Receiver pressure now in the scenario B is 40. So fall under which category? Scenario 1 or 2?
2 because it's lower.
Lower. Then you use this one. Lower means the P throat here will equal to P star. You understand? Means if your pressure here, your pressure inside here is less than 53.3 or P star, your throat pressure here will equal to P star. So what is the value of P throat in B condition? Cool. What's the value here? What is the value if you are in the B condition where your receiver pressure equal to 40 kilopascal? What is the pressure at this location?
Five 3.3, right?
Correct. Okay. So I believe all of you understand what is happening. So you have two scenarios here. One is this one is this one. So if the first scenario, you look at this one. If second scenario, you look at this one. So we solve for the first one first. So the scenario A is 80 kilopascal. So it's the first scenario. Your P throat here will equal to receiver internal pressure. This one. So you use the equation of this one. P throat over P0 equal to 1 over K plus something power K minus 1. Substitute the value inside there. You get the Mach number value. Because inside this equation, you do not have Mach number value. You have the K value. You have the throat value. You have the P0 value is the atmospheric pressure. Okay. So inside here, this equation, only one parameter missing, which is a Mach number. So you substitute all the value, rearrange the equation, you get Mach number at throat is 0.587, which is Mach number at here, Mach number equal 0.587. Okay, move very fast. So once you find the Mach number already, you can solve all the question already. You substitute back to density ratio. You get the P throat because the density of air you know. Mach number you know. K you know. You're only missing of a density at throat. Then the temperature at throat also same. You have the Mach number. You have the temperature of the atmospheric pressure. It is 15 degrees C. However, convert to Kelvin. Right? So substitute, you get T throat is 269 Kelvin. You do the same for second scenario. Okay, then the next one is to find the velocity. You have the Mach number. You know the R value, T value, K value. So you managed to find the velocity actually is 193 meter per second. I already proved to you why this Joule per kilogram square root equal to meter per second. I already proved in the previous class. If you miss it, go back to the previous lecture and listen to it. Okay. There's one particular slide that I do conversion about this one. Okay, so velocity at throat is 193. You do the same for, okay, then you determine the mass flow rate. You have the density, area, velocity. You can find the mass flow rate at the throat is 0.2 kilogram per second. And this is the answer for T versus entropy graph. So this is a T throat. This is the A scenario. This is the B scenario. Okay, there's a A and B there. So have a look into it. Okay, it's quite direct. If you compare the answer side by side, then you know how to plot this graph. Okay. You do the same for B as your revision. As a revision. You don't need to send me this one to me. Just do a revision. Okay. Solve using this graph, you get P throat ratio, this one, Mach number equal to this one. So once you find the ratio of P, move from the left, touch the first line, move down, you get the Mach number at the throat there. This is how you apply the graph. Then you move up a little bit, extend the graph. From the same Mach number, you move to the left, you'll get the throat value. I label as green color, then you can find the density with the blue color, this one from the graph. Substitute, you find the temperature and density. Velocity, you get 194 meter per second. Okay, so this is how you do it by using graph method. The first one is using mathematics way. The second one is once you find the Mach number, you enter the graph from using the pressure value. Then you get Mach number. From Mach number, you get temperature and density. Okay. So I think you can go through my PowerPoint slides later on for all this. This is a case B answer. And the rest you can go and view during your revision time. Let me end the recording.